So basically our previous discussion has led us to this problem. Yeah, that so this is the problem. Okay, problem is if n is co-prime to 10, okay, so you don't have to worry about this condition too much. This will just, you will see, get this naturally. Okay, then show there is some power of 10 maybe some power L, yeah, L of 10, such that n divides 10 to the power L minus 1, or that's the same thing as remainder is 1 when n is 10 to the power L is divided by n. Yeah, so we have seen how this is really needed for us to, finish that reasoning, right? Yeah. Or yeah, let's keep it simple and just think about this. And you can see that this is kind of, again, Pigeonhole principle, in the sense that we want to just show that there is something, some existence. So basically, you see from this, I mean, so don't take L to be 0. Okay, otherwise it's obviously true. But apart from that, we want to look. So we have this list of numbers, many numbers, like this infinite actually. We want to say that, yeah, we want to say that one of them leaves the remainder 1. Yeah, show that one of them leaves remainder 1 when divided by n. You can take n to be any number. You can take n to be some 47, let's say. Doesn't really matter. Okay. The argument should remain the same. This is a very interesting application. Many problems of divisibility that are done by Pigeonhole principle all have this similar idea that you will see here. Okay. So it's a theme in that sense. So one of them is going to leave a remainder 1. Let's see. So any ideas? So can you at least tell me that there will be two, can we at least say that there will be two numbers in this infinite list which have the same remainder? Can we say that? Right? Because what are the possible remainders? Yeah, the possible remainders are 0, 1, 2, 46. And if you keep taking numbers, then obviously you will meet two numbers which will have the same remainder. You don't even have to go too far. So how far do we have to go? Yeah, that's n, and so we can go till n plus 1, right? But here let's just take 47. Yeah, so if you go till 47, then you're going to find two numbers which have the same remainder, right? So there is, or there are two numbers, there are, and this is the key, okay? You don't get it directly, that leaves the remainder of one. There will be many questions like this where you won't get it directly, but you apply Pigeonhole principle and then you take it forward, you'll see it later that you get it. So there are two numbers, 10 to the power a, 10 to the power b, which leave the same remainder when divided by 47, okay? Which leave the same remainder, right, when divided by 47. So don't worry, it looks a very clumsy language. I'm writing too many words here, but that's because we have not introduced modular arithmetic, okay? But I would say let's do it like this first, and it will come naturally. When divided by 47, yeah? So what can we say from there? And so far, is this clear? This is, remember, this is the type of arguments you have to do in divisibility questions. If to take on remainders, you have to do simple problems will be done like this. This is the first step, I would say, usually, but there is no hard and fast rule, obviously. So what could we say about the difference between those two numbers? So you see 10 to the power a when divided by 47, so you use 47 here, divided by 47. This leaves a remainder, some, we don't know what remainder. That's the point of Pigeonhole principle. You don't know which hole two things go into, but there are two things which go into the same hole. And then there is other power, but that's the same remainder. So what can you say about the difference between these two numbers? So what can we say about the difference? I mean, in terms of divisibility, obviously, what can we say? So just try subtracting the numbers and see what you get. Do you get something interesting? That is also there, certainly. That is what you get. No. Sorry. So that also you cannot really say for sure, but let's just subtract and see. When you subtract, you get this, but then Q1 minus Q2, you just get that Q1 minus Q2 has to divide this big thing. But that doesn't mean that it has to divide 10, because this again will have other factors. Yeah. I mean, so you can just assume that A is bigger than B. That's not a problem at all. But that's not the point here. The point is that 47 has to divide. 47 is in the spotlight, right? 47 has to divide this thing. That is what we can say, and that is the key thing. It's not about the quotient, yeah, that we don't know, just like we don't know A and B. Okay, does everybody see this? This is the key about connection between remainders and divisibility. Same remainders imply is that the same thing as saying the difference is divisible. Yeah, that's why the theory of remainders plays such an important role. Because when we are interested in divisibility, we are interested in the remainders, not in the quotient. And just we can do an arithmetic on remainders, forgetting the quotient completely. And that is model arithmetic, which we'll see later maybe. So do you guys see that 47 divides? Does everybody see that? Huh? Okay, good. So then from here, can we say anything? So we have this 47 and we have this 10 to the power. So this will be some, so what will this be? So you can just take B out, right? If B is less, that's the maximum you can take out, right? You can't take out more. It's B. So from here, can we say something more specific? So it's 47. The number is 47. It is co-prime to 10. That was the initial standing hypothesis, and 47 is that kind of number. Yeah, in the sense that it will have no factor with it at all, right? It has, so 47 will have nothing, no factor in common with 10 to the power B. So everything has to be done by the other thing. Is this okay with everyone? Please tell me. I don't know because I've not done any number theory with other people. So I don't know. So you have to tell me, right? There are two numbers here, right? There are two numbers, but this 47 has nothing to do with 10 to the power B. It has no factors like 2 or 5, right? And it's a prime, so that is directly you can say. So there you go. So are we done? Right? We are done, right? This is the thing which we wanted. This is what means to say that 10 to the power a minus b. So we don't know the a and the b or a minus b, but we know that there is some a minus b. This leaves a remainder of 1. I mean, that's the same. This is the same thing, right? Because this means that 10 to the power a minus b minus 1 is 47 times something. You bring it that. These are the same things, obviously. All same. This is what we wanted, right? That there is some power which leaves, that power was not a or b, okay, but it was a minus b. There's some power which always leaves a remainder 1. That's a very beautiful thing, right? And obviously we need n to be co-prime to 10, otherwise that does not happen. You can think why. Yeah. So more number theory will help you to precisely know what that power is. We have just combinatorially figured out that power that there is some power, but more number theory is needed to just describe that power in a different way. Okay. And then the whole theory about smallest power and primitive roots and all the elementary number theories for understanding the smallest power in some sense. Yeah, that's what I was coming to. Yeah, because that is so certainly we have used the co-primality in this. Do you guys agree? Yeah. So, but obviously that doesn't mean that it has to be co-prime, but we have used it. Yeah. Everywhere, if you just consider this replaced by n, this replaced by n, and n being co-prime to 10 to the power b was critical to our proof. Yeah. So we have used it. But then it is not hard to see that if n is not co-prime to 10, then there is no chance. Let's see. So that's done. But let's say that let's just take it like this. I mean, if n is equal to 2m, let's say n is not co-prime to 10. Okay, let's say n is equal to 2m. Then can there be an L such that 2m divides 10 to the power L minus 1? This is plain wrong, right? This is an odd number. It's not possible, right? So n having a factor of 2 is doomed. Then there cannot be such a power. And if n does not have, and also if n has a factor of 5, then also same problem. I mean, this can have nothing to do with 5, right? It's co-prime to 5 because you can see this. How can this have a factor of 5? Yeah, because if this was divisible by 5, but then 5 also divide this, that implies 5 divides 1. I just did a formal argument, but you can see that it is obviously. Because you can subtract, right? If 5 divides this, 5 divides this, 5 divides the difference. So certainly, I mean, you need coprimality. Okay. You need coprimality. Okay. Well, what we have just done is the same question about the decimal expansion. These are the same questions actually, but maybe you don't see the relation directly. And let me not try to show it because that will just be just trying too much. Let's just treat this as a problem and we are okay, keeping it like this for now. I think this is good for us. So in the reference, I had told you Arthur Angel, okay. Brualdi, okay, I have the book now, I can see, but Arthur Angel is okay. That first 12 sample problems that I had, in that there are many divisibility and periodicity questions. Not many, maybe 2, 3 are there. Just see them, okay. I will maybe discuss them next time. Okay. So let's just take 5 more minutes. Okay, let's try to do another question. Okay. So this is about just the kind of the opposite of what we have done, or rather the complement of what we have done so far. What we have done so far is, we have looked at rationals and their decimal expansions, right? And the periodicity, yeah, if the periodicity starts from the beginning, then n is coprime to 10. And if there is a initial non-periodicity, then n has a multiple of 5 or 2, which you can see in examples, and we also saw a glimpse of kind of a proof. And that was the same thing in some sense as what we saw later, right? That there is that power which when you do, which leaves a remainder 1, which n leaves a remainder 1 when divided by 10 to the power L. And because that is what leads to your length of your period, right? And so on, okay? And that L, if that L does not exist, then you can see that there will not be periodicity from the beginning, which I have not proved. But they are simple enough, but we'll see them later. They're not simple enough, slightly. But basically we did 2 equivalent questions one was in a simpler setting, and the other because we are not too comfortable with decimal expansions in some sense. That's why. Okay. But now what is the complement? The complement of this is to look at numbers which don't have any pattern in their decimal expansion. The irrational numbers, right? And let's see what we can say. Yeah. So, and there also Pigeonhole Principle helps you to prove that's a serious theorem, which we'll prove, but the proof is simple enough. Okay. So decimal expansion. No. So there cannot be any period. Yeah. Which is it's easy enough to prove. We'll see. Decimal expansion of irrationals. Yeah. First of all, it's a very tricky thing to actually define irrationals. Okay, we will just say something which is not rational. It's a bad definition, but yeah, something which cannot be written in the form m by n. It doesn't really tell you anything. That definition is completely bogus. It's some sense of bogus. It doesn't tell anything. But then that's what irrational numbers are. Irrational numbers are, there is no constructive way to say something is irrational. Okay, you have to always go by contradiction. But the point is that if you take an irrational number, so let's say root 2, or any alpha, denoting it by alpha, what am I trying to say initially? Initially, I'm trying to say that it cannot be written in the form m by n. Let's keep that as a definition. Okay, cannot be written as the form, which is, you guys know that's the definition. Cannot be written in the form m by n. But the reason why it's a bad definition is, yeah, anyways, leave it. Yeah, some different things. Okay, but the point is here we want to say certainly that in the decimal expansion there cannot be a periodicity, because well, if repeat themselves at some point, if you say that there is a periodicity, so there is some after some L, now it could be very, very long, but some L, if there is some finite L after which there is a repetition, and there are a lot of things we are keeping under the rug, but yeah, if this happens, so then something is terribly wrong. Exactly. Yeah, then it can, because from here you can again do that technique and you can write it as m by n. Yeah, this implies that can be written as m by n. Just multiply by 10 to the power L, blah, 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 subtract, and you see you'll get can be written. So what do we get? We get that there cannot be a period. What do we mean by period? Period means that a certain consecutive thing of string of numbers that keeps repeating itself all the way. That is the definition. Now you cannot say that okay, there is some string which repeats itself for once and then repeats again. It repeats 10 times, but after that stops repeating. No, that's not period, right? Period means something that keeps repeating. So that cannot happen. Okay, irrational numbers, or I should just say that numbers that cannot be written in the form m by n cannot have that period. Otherwise, it can be written. So that's simple enough. Right? But that was not what I was having in mind. This is okay. This doesn't need any pigeonhole principle. Okay. So yeah, it doesn't have a period. Now, what does that? So like, what are the decimals? What is a decimal expansion? Like, what can we say about this? Okay. Well, if you look at a rational, right? If you look at a number like m by n, yeah, then you know that if you kind of it has a decimal expansion which kind of repeats, and then you know that if you take this 2 by n, 3 by n, dot, at some point you get an integer, right? If you take this multiplications, yeah, you get an integer. And if you, I mean, then it just stops, right? Then there are no decimals, yeah. So basically you can get only finitely many different expansions, right? If you start with this rational and you take 2 times this, 3 times this, and this, then it just stops. After some point, you stop, and then you don't, well, it does not that it stops, but the point is that if you take n plus 1 times m by n, it's not the same number as before, but my point is that it doesn't have any new decimal expansion, right? M is the integer part and the other is what you already had. So you don't get any new decimal expansion, right? There are infinitely many decimal expansions, and these are the ones. Because after that, the decimal expansions don't change, they just cycle up. Okay. But we want to say that for an irrational number, something very opposite happens. You get infinitely many decimal expansions. Yeah. So what do I mean? I mean that if you take root 2, then you take 2 times root 2, you take 3 times root 2, you take 4 times root 2. You see all these, the decimal parts of all these are going to be different. Yeah. Can you guys see that? Decimal part of all these above are different, like, because again you can just subtract, right? If 2 of them had the same decimal part, then you can just subtract and then you'll get a fraction for root 2. Okay, so just to write it, that's just the same argument we have seen, so there's nothing new here. If if n by n root 2 and m times root 2 had the same decimal part, then the subtraction would be an integer, and then that would be problem, some k. Then you can write it as a fraction. Okay, so this is a very interesting thing, because you see, rationals may, when you take the integer multiples, there are reasons why we do it. But if you take this integer multiples of a rational, then you get different, but then after some point it doesn't get more different. You just cycle back. Okay, that happens for rational, but for irrationals, it doesn't happen. You see, it's a two-way, it's a both-way thing. Okay, that's the beauty. So you got, these are all different, but we want to say something more. We want to say that the decimal part can get arbitrarily small. As small decimal parts as you want, you can get. So that's the thing. That's the problem, which if you take this list, okay, then one can get, this is not how it will be. Let me just put it as a problem first, okay? Show that there is a m such that the fraction part or the decimal part, okay, such that decimal part, this is called the fractional part, fractional function. If you guys would have seen it, if not, it doesn't matter at all. Decimal part of m root 2 is has, or rather I should say, decimal part of m root 2 starts with 10 zeros. Okay, so what I'm saying is that, or rather I should say, starts with at least 10 zeros, but that's, I'm not wrong if I say starts with 10 zeros. Okay. Yeah, maybe I'm wrong. I should say at least, but yeah, you understand. Yeah, I'm not saying it's exactly 10 zeros. Okay, I'm saying at least 10 zeros. And yeah, I cannot say exactly. Yeah, at least 10 zeros. So if what I'm saying is that there will be a m such that initially you will have 10 zeros. And this is again the first foundation of a series of problems which are of this type, which I have seen in Olympiads and also in theorems and so on. Okay, in contests, and these are made into some big theorems later on. At least this. After that, there will be something, but this will come in. Okay, this is a very interesting statement, right? You can check it on a calculator also. If you take root 2, 2 root 2, 3 root 2, you just keep taking. The numbers are not becoming small, right? It's actually becoming bigger. But there will be some big number whose decimal part will be very small, like this. And you can understand, I can replace a 10 by 10 to the power 10 also. There will be that decimal also. But let's just take it one ahead. This is the challenge. How do you show that some multiple will have this small decimal part? Again, this m will come as a difference. We will have to show that two multiples have the same decimal part. That doesn't make sense because they don't, but we have to say in some sense. And then the difference, the zeros cancel out or something. So this is again a new type of questions. I'm not expecting that you can get it directly. So maybe, sorry, what is happening? Allergy. So maybe keep this for homework, right? And think. Yeah, it's not simple, but just try to think and see. One second. Yeah. There will be some multiple which will be very, very small, for which the rational part will be very, very small. Okay. So think about this. Let it sink in. Okay. Yeah. I'm just thinking how I would have said it. So if I, oh, say okay. So let's stop here. Other than I would just want to finish that one triangle question, right? That was simple, right? So let's just finish that. Then we can stop the class, right? So I had asked you guys to do this. That if there is a equilateral triangle of, because this is simple, we should do this completely. Length 2, side length 2. Yeah, we had 17 points, right? And I asked you to show. Sorry, there are. What was the question? 5 points. Uh, okay, that one we did, right, by dividing again and again, right? So if that was a question that there are 2 points which are a different distance less than half, two points, distance less than half, that we did. But I had asked a variation to that, right? Huh. Yeah. So that was simple. But now I want to ask, rather I asked last time only, is that there are 4 points. Rather, there are 5 points. No, 5 points. Yeah. There are 5 points such that distance between them, between any two of them, then is less than 1. Did anybody do this? So this is like a, let's see first, and you can say. So we basically want one hole or one cage, one region to have 5 points. How could you guarantee that? Hmm? No, 5? How do you, no, but in that case, you don't get 5 dots. Mhm. Yes, right. So there will be 2 points in a small triangle, but how does that give us 5 points? Yes, so you can say it like that, but well, that's not a very correct way to say, because you want to, so even initially the reason you have given is not completely correct. So you are saying that let's just forget about 5 points and do the reasoning for 2 points once. Okay. So if you have 2 points, you want to show that distance is less than half. So the reasoning you're giving is slightly incorrect, in the sense that you're saying I am going to place 1 point in each of the 16 triangles, and then 17th point has to go in a triangle which already has a point. That argument is slightly incorrect. Okay, because you have to show that no matter how you place the points, 2 points will end up in the same triangle, right? Or with distance less than half. You cannot say that I'm going to place it like this. No, you have to say it in a way that no matter how you place it should work, right? So obviously what you're taking is like the worst case and still 2 points are ending up in the same triangle. So it's fine. In common sense wise, it's fine, right? But logically it is not fine. Okay. So logically you have to just say that there are 16 cages or 16 triangles, 17 points, the two of them, at least two of them will go in the same. Okay. That is yeah. So when you reason it like that, then it becomes not so clear that 5 points will go in the sub triangle in a triangle like this, right? Yeah, because then it becomes a little shaky. Okay, but still, I mean, but the point is that if you want to reason for those bigger triangles, then why do you even need to take the subdivisions? Further subdivision, just keep it like this. Just keep it like this, and then you say I'm throwing 17 points in these 4 places. Why should we restrict pigeonhole principle to n plus 1 pigeons and n holes? We have to take the next step. We have to take the next step now, right? Now there are 4 cages and there are 17 pigeons, right? Or there are 4 regions and there are 17 points. If there are 4 regions and 17 points, then can you say that 5 of them will go to the same? Yeah. So we have 4 regions. We have 4 boxes. You can think of it in whatever way is convenient for you. Yeah. 17 points. So this implies that 5 of them have to go to one region, right? At least 5. You can reason it in contradiction. You can say that if 4 goes to each, then you don't have enough points. Then you don't have enough. Then you only cover 16 points. Is it okay? Yeah. But you can say it in many other ways. So you can say that the average number of points is 17 by 4. So if the average of 4 things is 17 by 4, then at least one guy should have got at least 17 by 4. I mean, at least one region should have got at least 17 by 4. Otherwise, how could the average be 17 by 4? Right? So at least one region would have 17 by 4 points. But then if it has 17 by 4 points, it should have 5 points, right? You cannot have. So you can say it in that way, right? So you can say it in many ways. And each of them will lead to different generalizations. This average thing actually leads to a whole theory called probabilistic method, which later on, when you have more things about expectation and so, then it becomes interesting. So that's basically pigeonhole principle combined with another technique called double counting. Wonderful. Just many problems just become so simple with that. But anyways, this is okay. So then it's done. 5 points. And so we are okay. Yeah. So with this we shall stop. Let us just stop here. I have the book. I will from Bruvaldi also. I will recommend some problems to try. At the rule of thumb, I know that first 5 problems can be tried with what we have done, but still I will have a look and see. Okay. I don't remember the exact, but yeah. But see, you guys should understand that I am trying to do the variations. Okay. But I'm not taking arbitrary variations. I'm trying to do those kind of questions which will highlight some things, highlight some features, and obviously trying to do from different areas also, one from number theory, geometry, so on. But also they are highlighting some principles. Okay, some strategies which will you will, so you shouldn't just forget them. I'm not saying you have to learn them, but yeah, keep them in mind, then you can build on them. That's how I've chosen this. Okay, so they're in a certain abstract setting, but yeah, they are like theorems in themselves. So yeah, have a close look at these things. Okay, and today I've not asked many questions to try, but as I said, from Arthur Angel, try them if you get time, and also suggest from Dualdi. But look at these things closely. Note them if you've noted down or if you can see it later. But these are the, yeah. Okay. Okay. Try to